So to recap, we have reconciled the problem of atomic orbitals and VSEPR and bringing them all together to explain chemical bonding. We've reconciled that with the notion of atomic orbitals that are hybrids, so hybrid atomic orbitals. And this is really the central part of valence bond theory. And we've done this with many different electron domains, 2, 3, 4. We've even taken a look at 5. It's equally applicable to all those scenarios to help us rationalize why a bond should exist in the first place. But it can go a lot farther. And I want to consider a couple of special cases in this particular lecture. In particular, I want to think about lone pairs. Right? We were careful not to think about lone pairs specifically last class. We talked about molecular geometries where all of the electron domains were bonding domains. But what about lone pairs of electrons? Well, the good news is that they're really not different at all. It doesn't really take much extra to think about lone pairs of electrons using valence bond theory. Even though it's a theory meant for bonding, lone pairs fit into it just fine. Let's think about the water molecule as a pretty prototypical example. You will all know that the Lewis structure for the water molecule can be written like so. With a couple of bonding domains here, and let's not forget the lone pairs, right? So there'd be 2 lone pairs on my oxygen atom here. And so this is the Lewis structure. And we could walk through the same sort of arguments we walked through last class. For example, the electron configuration for an oxygen atom would include 1s2, it would include 2s2, and it would also have electrons in the 2p, 4 of them to be specific. So this is the electron configuration if I were to make an analogous electron energy diagram. And by the way, we don't always have to do this to do valence bond theory. I'm explaining it in a way that I think is the most explicit. I'm trying to go into the most detail to maximize understanding, but one does not need to do an energy level diagram to rationalize the behavior of these orbitals in terms of valence bond theory. But if I did do an electron energy level diagram, and I knew that there were 4 electrons in my oxygen atom, in the P's, then I'd get this. And potentially confusing in the sense that we can see 2 electrons available for bonding, and we have 2 bonds. So we might question the necessity here. Do I need to go to valence bond theory? And the answer is yes, you certainly do. You need to go to some sort of bonding model. I mentioned there were 2, but we haven't gotten to the second one yet, because this 2p set of orbitals, remember, they're at 90 degrees from one another. One of those is potentially a 2px and a 2py, or a 2pz and a 2py. I mean, it doesn't matter which 2 they are perpendicular to one another. And we know that this oxygen atom has a tetrahedral electron domain geometry. Tetrahedral because it's got 1, 2, 3, 4 electron domains. That's key. And so we know that this bond angle here between the 2 hydrogen atoms is close to 109.5, likely a little less than 109.5 because of the added repulsion from these lone pairs. So this still doesn't explain it. And so we'll do the usual thing with valence bond theory and creating hybridized atomic orbitals. And we will realize that if we have 4 electron domains, we must create 4 hybrid orbitals. Nothing about that rule changes. And so if we create 4 hybrid orbitals, we've already done this last class, we know that the result will be 4 sp3 hybrid orbitals. And in this particular case, we've got 6 electrons. So if I populate this diagram, which I don't necessarily have to do, but if I do just to have a look, I can see that I've got 2 of the sp3 orbitals completely filled. In other words, those are the 2 lone pairs. They are completely filled. They are not interested in bonding. And these are the 2 bonding electrons. They are lone electrons by themselves in an orbital, and that is an ingredient that is required to make a bond according to valence bond theory. At least, one electron. Two represents a full orbital, and therefore a scenario not able to create a bond. So here we go. Here are our electron pairs, our lone pairs, represented here. And we have each of our sp3 orbitals able to make a bond with a hydrogen atom. And that, of course, would be a sigma bond. Here is a graphical representation of those orbitals themselves. So here we can see one of the sp3 orbitals. Of course, there are 4 of them. I can point to them if you like. There are each of the 4 sp3 orbitals, and I can see that 2 of these electrons are existing in one of these sp3 orbitals, the other 2 over here, and then I've got my overlap between the other 2 sp3 orbitals and the 1s of each of the hydrogens that are being bonded. And so this is why we can say that the water molecule is actually tetrahedral. It's tetrahedral in its arrangement. Its molecular geometry is bent. We talked about this when we talked about Vesper, but it's tetrahedral because its electron domains need to be distributed in a way that is as far apart as possible. And so it will have a couple of sigma bonds signified here by the overlap between the hydrogens and the sp3 orbitals. So that's lone pairs. Really nothing new here. That's good news for us. I'm just sort of stressing the fact that lone pairs are treated in valence bond theory in exactly the same way as all other pairs of electrons are. Now, what about multiple bonds? This is a scenario we haven't treated explicitly quite yet in this class. Multiple bonds. Let's think of cases like C2H4 or ethene, the ethene molecule. What does the Lewis structure look like for this molecule? Well, we can propose one that would look like so. And this is indeed the correct Lewis structure for ethene, C2H4. And the question is, how does valence bond theory work, and how can I reconcile the atomic orbitals for carbon in a scenario like this, recognizing that it's different really than previous examples we've talked about because of this double bond? And what does valence bond theory have to say about this double bond? Well, it actually has to say something that's very, very relevant. Let's again remind ourselves about what we need to do to create valence bond theory like hybrid atomic orbitals. I'll go through the pain again of indicating the electron configuration for this atom. Again, this is a carbon atom. I know that there are 2 of them, but fortunately they're both equivalent. It doesn't matter which one I pick. The electron configuration is the same for both, as well as the current molecular environment for both. They're completely identical. So pick one, and we'll assume that that's the one we're treating here. Now, the energy level diagram that we frequently draw for these, which is again not required but helpful for the purposes of illustration. Here we go. We've got our valence 2s, our valence 2p. We know that there are 4 electrons in this system. And so the question then becomes, how does valence bond theory treat ethene? Okay, so here's what we do. It's the same exact treatment, fortunately, but there's an interesting conclusion that can be drawn from it. We count electron domains. Always the same. That part hasn't changed. So around the carbon atom, I have 1, 2, 3 electron domains, recalling that a double bond is still just a single electron domain. So with those 3 electron domains, that means that I need 3 hybrid orbitals. All right, so in this particular case, I'll need 3 hybrid orbitals. Again, I always start with the s and then take as many more as I need. And so the result in doing this will be the creation of 3 sp2 hybrids, just like it would always be if we had an s and 2 p's, sp2 hybrids, and of course a remaining unhybridized 2p orbital. Okay, so this is the scenario, and I know in this particular case that I need to make at least 3 bonds. Okay, So I need to make a bond to the other carbon atom, I need to make a bond to the hydrogen atom, and I need to make a bond to this hydrogen atom. So if I put all 4 of my electrons down here in these sp2 set of orbitals, I'll have 1, 2, 3, and then a paired one, which doesn't make a lot of sense in this context because I don't have any paired electrons here as lone pairs. So for the purposes of illustration, it's also useful to write all 4 of my electrons as being separated here. Now, this is an unintuitive thing for most students to do, but what I will do is remind you that this is not a real state of the carbon atom. Valence bond theory is a human invention. It is a technique we use to rationalize the existence of this structure and help us learn something about it, help us understand what the properties of these bonds might be. And I'll get to that in a minute. But specifically, placing electrons in this diagram is not something that's explicitly useful in and of itself because carbon doesn't exist in this state. We envision it being in a hybridized state for the purpose of creating these bonds. But this is the state that it exists in. So, what can we do? How do we interpret this? Well, we've got 3 sp2 orbitals that will be distributed as all sp2 orbitals are, and that is with a direction of 120 degrees between one another. And isn't that precisely what happens in ethene? We know that with 3 electron domains, we should have each of the domains separated by 120 degrees each. So there should be about 120 degrees between each of these bonds. And we already know from last class that sp2 orbitals, of course, achieve that. So that's great news. But what does it mean for this double bond? Well, each carbon atom will be represented identically. And so the sp2 orbital that extends from this carbon will overlap with the sp2 orbital that extends from that carbon. And that will be sufficient to create a sigma bond between these 2 carbon atoms, as well as a sigma bond between the carbons and all of the hydrogens. But the interesting piece here is that there is a leftover 2p electron. And more importantly, there is a leftover 2p orbital. Let's consider the implications of this. Here is a diagram of precisely what I've been talking about. We have a carbon atom with 3 sp2 orbitals distributed in a trigonal planar arrangement around the center. And I've highlighted this plane with a plane. And you can see that these 3 sp2 orbitals are being cut by this plane. Likewise, we can see our hydrogen 1s orbitals, and therefore we can clearly identify where the sigma bonds are in this particular species. We can see a sigma bond formed by the overlap from this hydrogen atom with the sp2 orbital of this carbon, likewise over here. And of course, we could say the same thing about what's going on the other side. These are also sigma bonds. And just to be clear, the overlap between the sp2 orbitals of each of the carbon atoms is yet again another bond. And because this overlap is happening at a single point in space, we again call this a sigma bond. In other words, our representation of ethene here so far has 1, 2, 3, 4, 5 sigma bonds. But now is where things get interesting. Let's not forget that there is a leftover electron in each of the p orbitals of these carbon atoms. Let's glance back at the diagram we've just left. I took the time to highlight the fact that I've got a leftover electron that is in the unhybridized p orbital of the carbon atom. And of course, both carbon atoms are the same. So what this results in is a scenario where these leftover p orbitals that have been completely unhybridized have an electron in them. This is important. First of all, I'll remind you that the entire orbital you see here in pink, that entire orbital is one orbital. That's different than when we were thinking about these sp2 orbitals. These large lobes of the sp2 orbitals are themselves a complete orbital. Each one of them is a different orbital. whereas this p orbital is a single orbital in and of itself. So it spans across both sides of this plane. And of course, the same thing can be said for this other carbon atom. Now here is the scenario we've got. We've got an orbital that is half filled directly next to yet another orbital that is half filled. And that is exactly the scenario that we say gives rise to bonding. The overlap of those two orbitals will be the creation of a bond. But what is interesting in this case is this is the first example we're seeing of a bond that can be formed between orbitals that aren't hybridized. There was no need to hybridize 4 different atomic orbitals because we only had 3 electron domains around the carbon atom. And that very serendipitously created our trigonal planar arrangement here. And we've got 3 sigma bonds along a plane for this carbon atom. But we've got this leftover p orbital on each with a leftover electron. And it is certainly true that what will happen in this case is each of these p orbitals will lean into the other and overlap, both on the top and the bottom of this plane. In other words, this is a unique scenario where overlap between these orbitals can happen in 2 places, on the top and on the bottom. I've got another diagram to illustrate this for us. In this diagram, we can see exactly what I'm talking about. I've removed all of the orbitals that create this network of sigma bonds, leaving the p lobes and their leaving the p orbitals and their lobes to be shown by themselves. Now, the point I'm trying to make here is that there can be and there is overlap between the lobe on the top with the lobe on the bottom. And what's interesting about this is this can be considered to be one bond, right? There is one bond here, and we have a special name for this, which is being indicated here in the figure. To differentiate it, because this is not overlap in one place, like all of the sigma bonds were, this is overlap in 2 places. And we have a special name for this, as the slide indicates. This is known as a pi bond. Okay? Now, interestingly, this is, I want to be clear here, this is one pi bond. We remembered that there was an electron in this p orbital. There was a second electron in this p orbital. So we have a grand total of only 2 electrons in this particular overlapped orbital. 2 electrons means 1 bond. So what you are seeing here in pink, in its entirety, is the graphical representation, according to valence bond theory, of 1 bond. Remember, though, that it's a double bond between the 2 carbon atoms, but the other one was the sigma bond we've already seen. We've already seen overlap between adjacent sp2 orbitals on each of these carbon atoms, and that is one of the 2 bonds in ethene. The second of the 2 bonds, according to valence bond theory, is this pi bond. And in general, that will always be true. When we see species that are multiply bonded, the second and any additional bonds after the first one is going to be of this type. It's going to be a pi bond. So a quick way to identify these is the first or single bond between all atoms is known as sigma, and any additional ones are referred to as pi. And the reason is because they will be formed without question by a mechanism that looks like this. And so this is what we call a pi bond. Now, this has very important implications, one of which is that in order to make this bond, you can see that we need to have overlap both on the top and on the bottom. In other words, if I were to twist this molecular structure around the bond or around the axis joining those 2 carbon atoms, I would break the symmetry of this top and bottom overlap. The pi bond would then cease to exist. In other words, according to valence bond theory, doing nothing more than twisting this ethene molecule could in principle break the pi bond. Not break the molecule apart, but break the pi bond. So if such a thing as a pi bond exists, and if it exists in the manner like valence bond theory seems to be proposing it is, then I would expect it to be virtually impossible to twist this ethene molecule around its axis. Here's a more explicit diagram of this same exact principle. We create a pi bond between overlap of adjacent p orbitals. Twisting around one end of that knocks the second p orbital out of alignment. And the conclusion or the interpretation here is that this should not be possible if we want to hold the pi bond intact. And in general, there are all kinds of examples of this being forbidden in chemistry. So we actually have experimental evidence that suggests that molecules that possess double bonds like this one, like ethene, and like so many others, are actually rigidly held in place, which is somewhat surprising when you think about the fact that all a molecule is a collection of charged particles flying through space in close proximity. What would be in place to prevent this hydrogen atom from simply migrating a little bit down? These are just particles flying in space. Well, according to valence bond theory, there is favorable overlap and favorable interactions that exist with these particles if they lock themselves into this particular coordination. This is an important implication of double bonds, and it gives us the rationale to say that double bonds are actually rigid chemical entities. We can't spin molecules around or rotate molecules around those double bonds, whereas we certainly could rotate around sigma bonds. That's all overlap in one place, and rotating around that bond doesn't do anything to affect that overlap. And in general, molecules with many, many single bonds we consider to be very, very floppy. Some of you will have seen long carbon chains written like this. So long as they are all single bonds, this is a very floppy molecule, so to speak. But more on that later. The point, though, is that valence bond theory helps us to rationalize why this is. Why or what properties floppy molecules should have as opposed to rigid molecules, that requires a bit more thought. But nonetheless, valence bond theory gives us the theoretical framework to understand that principle and use it to explain chemical properties. The final piece that I wanted to talk about today is something that we had addressed slightly when discussing Lewis structures, and that is the topic of resonance. Resonance is an incredibly important topic, in particular in organic chemistry, because it makes a big difference on all kinds of properties, most notably the stability of molecules. What resonance is, if you've forgotten, is really a scenario where multiple Lewis structures are not only plausible, but often equivalent. Take a look at these NO3- structures. It's clear that I can choose to put that double bond in any one of the three trigonal planar positions and get a virtually identical Lewis structure. Of course, procedurally, I would say that these are different because I would choose to put the double bond in any one of those particular places. But practically, aren't these all identical? They're all just rotations of the same exact structure. Should I really expect this particular molecule to have one bond that is qualitatively different than the other two? Well, maybe. What resonance says is that really any one of these isolated Lewis structures is in and of itself inadequate. Whenever you have many Lewis structures whose formal charges are identical and all other methods of discerning which one is best don't work, essentially they're all right. That's what resonance is saying. Resonance is saying all three of these are right simultaneously. In other words, there isn't really a double bond here and two singles down here. What there really is three singles and a 1/3 bond spread over all of the different bonds. In other words, this double bond can manipulate itself and bounce back and forth between all of those different positions. That's what resonance says is more like reality. Well, Lewis gives us a way to describe that, which is what you're looking at on your screen right now. It's a bit clumsy because we have to explicitly write out all three options and then indicate that they're resonance structures with these double-headed arrows that tell us, well, this is going to switch back and forth between this and switch back and forth between this. But even that interpretation is somewhat flawed, and I don't love it because it asks students to think about the notion of this double bond literally changing position and going over here, and then moving over here, and then moving over here. And that still conjures the notion of one bond being unlike the other two. And I think it would be better, and I think it's in fact more realistic, to realize the fact that all three of these bonds are essentially equivalent. And what we've got is a pair of electrons that is a little bit more migratory than the others. And we know that it can spend time in all of these places, so it's distributed more or less evenly over the whole molecule. All right, well, that's a mouthful. But what does valence bond theory have to say about this particular species, or any species like it? What it really says is that in these species, as sp2 atoms, we realize that they will have leftover p orbitals, just like those of ethene in the previous example. And those leftover p orbitals can interact and overlap with their neighbors. But what's interesting about this particular molecule, and there are plenty more examples like it, is that all of the atoms contain those leftover p orbitals. And we can more accurately envision the structure of a molecule like NO3- like this, where we've got a leftover p orbital on each and every one of the atoms, and a grand total of a couple of electrons spending its time throughout this entire network. This is a much more realistic picture of what the electrons are actually doing in this species. And it gives us a lot of information. It tells us that the electrons should be well delocated over this whole structure. And this actually has stabilizing effects associated with it. And so this structure and this way of thinking about things, the valence bond hybridized orbital way of thinking about molecules, gives us a really convenient picture for these resonance structures and allows us to conveniently imagine electrons spending time spread out throughout the entire molecule, because these leftover unhybridized p orbitals essentially provide a channel or a three-dimensional region of space for those electrons to exist in over the entire structure of the molecule. A much more convenient way of thinking about resonance. So back to one of our original questions posed when we talked about bonds. Why are trans fats so bad for us after all? And what does it have to do with valence bond theory? Well, I just got finished telling you about how these double bonds are so rigid. The double bonds cannot be twisted around, and that's a really important implication because we see them all the time in biochemistry. And what is a fatty acid? A fatty acid is nothing more than a long carbon chain. That's pretty much it, with maybe a couple of oxygens at the end. So these long chains of carbon we see in all sorts of foods. These are what fats look like for the most part. Now, how do they behave? Well, if it is a saturated fat, what does that mean? Well, that means there are no double bonds anywhere along the structure. In other words, it is saturated with hydrogen atoms. That's what a saturated fat is. What is an unsaturated fat? Well, now that's self-explanatory. It's one that contains at least a double bond somewhere. So those are our unsaturated fats, and those are our saturated fats. But what about those trans unsaturated fats? That's this one here in the middle. How does it differ from the cis unsaturated fats? Well, trans and cis differ in the direction that the hydrogens point. Remember, these are rigid bonds, so they can't be spun around. So this particular unit here is locked in place. Likewise, so is this one. And look what happens. These cis trans fats get this kink in them. And what that means is that these cis unsaturated fats don't pack very well. You can't put a billion of these things right up next to one another because they're kinked and they sort of get in the way. And what that means is that they're less dense. Now, contrast that with the trans fats. They're sort of locked in place. They're locked as these long, relatively linear chains, which makes them really easy to pack together, which makes them really dense and really amenable to clogging your arteries with these very thick fats, right? So trans fats tend to pack together much more tightly, and it's exactly because of the rigidity of this double bond. We can't spin this around and make it more kinked, and so these trans fats tend to pack very, very tightly and tend to be more solid and tend to be more dangerous when they're in our arteries. Now, these saturated fats, though, when we look at these, you might say, well, they're linear too. Yes, but there's no double bonds in them, so they're very, very floppy. In other words, you just heat them up a little bit, much like butter, and it melts and it becomes much more fluid and much more easily cleared from your system. So that's the difference between saturated and unsaturated fats, and stay away from the trans because these ones are dangerous and there's nothing that you can do to fix that because of this rigidity of the double bond. Why is it rigid? Ultimately, it has to do with hybrid atomic orbitals and leftover p orbitals that overlap to create pi bonds. That's why trans fats are unhealthy, because of pi bonds. There's got to be a joke about pi in there somewhere. But for now, let's call it a day and end our discussion of valence bond theory.